For the past 9 videos, okay, there's 1, 2, 3, 4, 9 videos, okay, I've been talking only about example 1, okay, so now we get example 2. What is the difference between 1 and 2? Is that 1, it is a num-pipe system, so what we have done for the past 9 videos, is num-pipe system, and what we're gonna do now is for pipe system. Okay, and we have to use polar coordinate. Just now we used Cartesian. So let's take a look. So previously we derived the Navier-Stokes equation, and then we derived the velocity of the particle over here. This Navier-Stokes equation uses x, y, and z, right? X, y, and z. So it is so it's in terms of Cartesian coordinates. For polar coordinates, in terms of one straight line and an angle theta, right? This is what it means. So for pipe you actually use polar coordinates. Another thing I need to let you know the difference is that non-pipe system you integrate, which is just now for the past 9 videos, okay, you integrate twice first and then you apply boundary conditions. For pipe system now, okay, now you integrate once and then you apply boundary condition, and then you integrate again and then you apply the second boundary condition. Okay, so where does the boundary condition come in? So at first we talk all about the Navier-Stokes equation. Let's use the Cartesian coordinates first. Okay, these are all the same. Okay, this is exactly the same what we have said earlier. And then this is the x-axis. Okay, we assume all are the same parameters. Okay, we didn't say, but we assume that it is steady state, so that t can be cancelled. It's incompressible, density is cancelled. And then assume 2D flow again. Okay, z is cancelled. And then we look at only the change in the x direction, so v is cancelled. So we derive this over here. Sorry. And then we have this one over here, right? And then we derive equation to estimate velocity of the free particle. If you remember, we actually assume laminar and free develop. So in this case, free develop means that it's flowing in a constant speed right now. Okay, it is flowing in a constant speed, so there is no changes. So although there is changes across the x-axis, this is the x-axis, right? There is changes across x-axis, but the changes are all the same, throughout the same. This is what it means. So therefore we can also take average of them, free develop, and you have a straight line, right? And then since we have this thing over here, since we can take average, there will be no variation across x in this case, because there is no straight line now. Okay, we can actually cancel off all the x components. Okay, cancel all the x components. Let away that the pressure gradient survives, because the pressure gradient, due to the Bernoulli's equation, there is other values. Okay, there is the pressure of the system. Within it, they have something. There is still the pressure within the system itself, so we cannot cancel away. So because in this graph we are talking about the velocity, but there is no pressure shown over here, right? But there is pressure across x. Okay, so just let you know there is pressure across x, and therefore we do a little things and we derive this one over here. If you remember, this is exactly the same. So once we derive over here, what we need to do is actually to change to polar coordinates. So this is where the changes comes in. So I actually take this equation out. So this is the equation. So from last lesson, just before integration. So last few lessons, last 9 videos, after we have this equation, we can straight away integrate, right? To find u, we integrate twice. But now, we have to integrate one time first. Okay, so we have to change to polar coordinates. Okay, change to polar coordinates. So how do we change, right? Why do we change also? It's because now we are talking about the pipe. The pipe is radius, right? So the radius, so this is the pipe. The radius can be across all these dimensions, is throughout. So imagine we have an x, y, and z. Then we have a pipe. So the radius takes in the z-axis and also the y-axis. So it's throughout the z and the y plane, right? So in order to describe throughout, you can actually use r and a radius and a degree. Okay, so whatever degree you want, you can actually use it. So this is the polar coordinates, r and a certain degrees instead of the x, y, and z, right? So this is what it means over here also. And then therefore we now use polar coordinates r and theta, since anywhere the same for radius r. I hope you understand this. If you don't understand, you just skip back a little and then watch again. So what I do is actually to change to r. I change this equation. This equation is what we have last derived, and then we put it over here. We change y to r, so we have r squared. Right, the rest stays the same. I didn't change anything. And then I rewrite. What I rewrite is actually to hold on. So what they did is actually to multiply 1 into the thing. So it doesn't change anything, but rather than it's r over r. So the r, so this thing is being separated into del r and del u del r. Okay. So this is the del r and del u del r over here, and then I multiply the r into this thing, while the 1 over r I leave it outside. Okay, and then after which I rearrange, I bring this 1 over r outwards. So I have over here. So this 1 over r becomes here, right? So this is what it is over here, right? The purpose of it, I have a little, I have no idea. But once you have this, you can actually set boundary conditions. Okay, so as you can see, we haven't integrated yet. We are just changing the coordinates to polar coordinates. That's all. Then now we set up the boundary conditions first. Now the r is equals to 0 when at r is equals to 0, which is at this point. Okay, u is equals to the highest velocity, right? Is over here is different from the plate itself, right? Sorry, I'm lagging. So it's different from the plate itself when you move, because just now the plate is moving at the top. Well, now the fluid itself is flushed into here, while it is constrained by this two portion over here, right? The walls itself restrain the movement, the motion, so therefore it is moving. So this restrain this, and this restrain this, and so on and so forth. So this is the faster over at the middle. So at r is equals to 0, u is actually the highest, okay, which is actually the highest. And then when r is equals to r, which is this point, this point is actually r. Any point along this line is actually r. Any point along this line is actually r. Okay, so u is equals to 0, and it makes sense because there is no speed over here. And if you were to take a look properly, it is actually a no slip condition. Okay, if it's a slip condition, you actually branch out, right? So there will be a certain velocity over here compared to the no slip. But we are always talking about no slip, so we are So we are chillax. Okay. So after knowing the boundary conditions already, now we can integrate and then solve for C, and then integrate again and solve for D. Okay, what it means is that when you integrate one time, this is what the equation over here is. Right, we just bring this equation and just bring it upwards over here. It's exactly the same, right, but I integrate them. So if I integrate partial over partial r, you have partial u over partial, you have this term over here left. This term is simply cancelled, right? And then when you integrate r, you have r squared over 2. The rest is simply constant plus c, right? Integrate plus c. And then I can bring this r over here. So I bring this r over here, I can cancel away the square. So this is why I have r over 2 over here. And this integrate one time, and then I solve for c when r is equals to 0. Okay, u is equals to the highest speed u. However, if it's partial u partial r is equals to 0, because when the radius always at a point, okay, there is how do I say, the velocity does not change, right? The velocity doesn't change at all, so there is no changes across partial u partial r. You need a certain value of r to have a certain changes across the u, across across a certain velocity u, right? So this is the this is u y, right? ur, sorry. So as r is 0, you have no changes, right? It's always this same speed over here, so there will be no changes. So since there's no changes, it is equals to 0, because this is just simply to describe the changes across certain r, but there is no changes in r, there is no changes in u. And then since r is equals to 0 also, okay, so this whole term becomes 0, therefore c equals to 0. And then you integrate again, okay, you integrate again, you take this equation, okay, taking the c out, okay, because you know c is equals to 0, you just sub it over here. Then you have plus d, right now a different constant. And then r divided by 2, you integrate, you have r squared over 4, right, this is over here. And then this is simply that. And to solve for d, because we want to solve for the constants of integrations, when you integrate you have certain constants. So this is what we want to do. This is why boundary conditions this is why we do boundary conditions, is to solve for the constants. And then so when r is equals to r, when the radius r is at this point, the velocity is 0, right? It's not moving at all, right? Because it's a no slip condition, right? At this point the velocity is 0, so therefore u is equals to 0, and therefore this is u, right? So u is equals to 0, and then when r is equals to r, so I just sub in r squared, so this becomes r, right? The first is r squared, then I sub in r, so it's r squared, capital R, and the rest stays the same. And then I just bring this whole piece, okay, I just bring this whole piece over here, so we have d. So d is equals to minus r squared over 4, blah blah blah. And then so we can actually form our final form by using this equation. Okay, this is the second order integration. Okay, we integrate 2 times back, and then we know our d already, you can just sub it in. So when you sub it in, you have, this is d, so you sub it over here. You have the same constant equation. So what are the constants you can actually factorize out? These are the constants. Okay, for del p del x, 1 over nu, 1 over nu. So the only difference is only r squared minus r squared. So I just factorize out all the constants. Okay, they are the same. And r squared minus r squared, we have this. So we have found a equation to describe the streamwise velocity component u of the fluid in the x direction. Right. So this is the thing. And then next video I'll explain a quick one on why we cannot integrate twice and then apply boundary conditions. Our answer is actually different. Okay, a little different. And then yeah. So I'll see you in the next video to talk about it. So yeah.